get that activated, so whenever we get to the Q&A and all that. But you can also join at the Q&A, and everybody understands that you can go ahead and join that slido.com and put that number in, right? If you ever can't do the Q&R. Okay. Okay. All right, so this is the overview of your most common elementary steps. It's like the little bridge that's going to take us into reactions. So these are sort of the common steps you're going to see in reactions. Think of them as the motifs, or like the steps in a dance, okay, or in a song. So the mechanisms are going to be predictive tools. This is, again, that proton transfer. We're going to go ahead and revisit that real quick. So opposite charges attract, like charges repel. We're all okay with that, right? Fantastic. The atoms in the first and second rows of your periodic table, they have to obey the duet on the first period, octet rules on the second period. I personally hate that terminology, and I like to just say noble-like configuration. Okay? But almost every book ever written likes that terminology and uses that, so to be consistent. Why did I not mention the third period, by the way? Yeah, we can actually form extra octet, right? 10, 12 electrons around it. And that's because we actually make, on the third period, the 3d orbitals. Those are available to do bonding in. You can put electrons in them. Okay? And that means you can pull more electrons into bonding orbitals. Okay? The fourth period does it more. It's a little more unusual on the third period to do that. But, yeah. Now, in organic chemistry, for the most part, we're going to be using the octet rules. And for hydrogen, of course, the duet rules. Okay? Now, this right here is electron-rich. It has an electron-rich site. And this is, of course, an electron-poor site. And so these are actually going to be attracted to each other, right? Okay. And once they get near each other, they can go ahead and do what's called a coordinate covalent bond. Were you guys aware of that? Okay. Anybody know what a coordinate covalent bond is? Huh? Okay. You're aware of covalent bond, right? So each of them shares electron, and they make a bond, right? Covalent bond. When only one provides the electrons for the bond, that's called a coordinate covalent bond. Okay? I'm going to act as if you need 2 electrons in a bond, because the research that shows that you can do carbon-hydrogen bonds with 1 electron is 2 weeks old. So we're going to act like that's not a thing, okay? Okay. However, know that is now a thing. It's very rare, so you don't have to worry about it. But it is a thing. Okay. So in this case, we have donated a proton, and now we have our chloride alone. That is the Q&A, by the way, in case anybody still needed that. Let's go ahead and solve a problem. So let's identify the electron-poor hydrogen atom in methanol, and we'll draw the mechanism by which the methanol would act as an acid in a proton transfer, reaction with H2N minus. Okay. So the first thing I'm going to ask you is, which proton here is electron poor? Which hydrogen is electron poor and would be the one that is going to end up being donated? Wait for it. Well, get ready in your head. Everybody ready? Okay, join up. Okay. So, does everybody have an answer in their head? You'll have 15 seconds to put it in. Ready, set, Which one would be electron poor? Okay. And it is the OH. And that's because OH has a much higher electronegativity, right? Okay. And so that's going to pull electrons away from the hydrogen, making it significantly more electron poor than the others would be. Now, the CH is actually more electron poor than the other two options. That's the second most electron poor one. The carbon will pull electron density from the hydrogen, just not as much as the oxygen. And that's why the CHs are more acidic than the other options there. The LiH is actually electron rich. Hydrogen is actually more electronegative than the metal. Yeah. That's actually how you can make hydride, which is the H minus, a negatively charged hydrogen. Okay? All right. So let's go ahead and do this problem. Now we're going to do the mechanism. So again, this one right here is the electron poor one, right? That's the one that would be acidic in this case. Here we have what would be considered an extremely strong base, right? Stronger than you would actually be able to use in water because it would end up being neutralized by water, right? Okay, and so we're going to go ahead and put these two together. And what sort of mechanism are you expecting? Okay, so what does this nitrogen look like first off? Has a nitrogen, right? Okay, and then it's bonded to hydrogens, right? Okay, is there anything else about it? Has a negative charge. How about lone pairs? Nitrogen normally has how many lone pairs? One lone pair normally. Yeah. And this time it's going to have two because it has that extra electron. Yeah. I'm going to put little tiny lines if that's okay. Can everybody see it okay? Okay. Yeah, it's very difficult for me to put dots. They don't show up well. All right. And so that's the nitrogen, isn't it? Okay. I'll put a little circle around the negative charge so it looks more like a negative charge, okay? Get separated. All right. So what happens? What does the mechanism look like now? Yeah, and which direction is the arrow, though? Yeah, we're going to move the electrons, right? So the electrons are going to go and attack this hydrogen. Everybody okay with that so far? Okay. How about the electrons that were between the carbon and hydrogen now? Can they stay there? Or I mean the oxygen and the hydrogen, excuse me. That bond there between the hydrogen and oxygen? Yeah, they have to go to oxygen, don't they? And that's because we're violating the duet rule, aren't we? We have more than two electrons around that hydrogen once we make that new bond. Okay? And that's going to cause the electrons that were around hydrogen to shift over to the next thing, right? Now, you typically will have to shift these until you get sort of the most stable thing you can get. Okay? Anybody ever heard of the oxyanion hole yet? No? Okay. Okay. So leave that in the back of your head and you can have that for whenever you go to biochemistry. I wasn't sure if they covered it in micro yet. Okay. So these electrons transfer over onto this oxygen, and that's the thing that's the best, most stable to hold a negative charge in this molecule, right? And so that's going to be the one that's going to end up with that negative charge there. Okay? Okay. This, by the way, are the same rules that you would use for assigning formal charges. So remember those rules that you assign formal charges back in the structure? Same rules. Okay? Most electronegative atom gets the negative formal charge, right? Least electronegative gets the positive formal charge. Okay. Now, they do have to go through bonds every time, right? So you can't just collapse over and over and over, and be okay. Okay, you would actually have to go, like, you can't get, over here. Because they aren't attached, right? The electrons have to go through the bonding structure to get anywhere. Okay? Okay, so far we got that. Everybody okay with that? Okay. So this right here is showing the movement of the electrons. That's our mechanism so far. We will go over to products through our reaction, and then we will state that we're end up in. Everybody okay with that so far? Okay. Does anybody have any questions why we end up like this? No? Okay, fantastic. All right. So, simple assumptions regarding the electron-rich and electron-poor species. The anions do not exist in solid or liquid phase without the presence of cations, vice versa. So when we have an anion-cation pair, it's going to be very difficult to have any significant buildup of positive charge by itself, right? Or any significant buildup of negative charge by itself. So there is an assumption that we'll always have spectator ions. We'll always have an oppositely charged ion that's going to keep that from building up a positive or negative charge, right? And that's the spectator ions exactly from Gen Chem, if you remember that. Okay. The metal cations typically are going to be the ones that we're going to use as our spectator ions because we're in organic chemistry, and we typically just don't care about the metal cation. That's basically the truth of it, okay? They don't make covalent bonds in almost any case that we use these things in. And so they're just going to end up ions and stay ions for almost every reaction we ever do here. Okay? And so typically we just ignore those cations and whatever. They don't matter. Okay? And we just assume that they're following along and neutralizing that charge the whole time. Okay? Anybody know what happens if you build up charge, by the way? It provides energy going the opposite direction. So if you build up charge, you'll actually halt your reaction. Okay? It's actually what happens in a battery, by the way. Is you build up charge on one side, and then it drives it the other direction. That's why you can do things like charging batteries. Okay? Most of them work off a charge differential. You can have ones that don't. But anyways, let's not complicate that. All right. So draw the necessary curved arrows for the proton transfer between KOCH3 and HCN in solution. What's this proton transfer going to look like? Which one is the acidic proton? Which one is the basic? You're good. You're good. Yeah, this is an example one. I'm not going to quiz you on it, but yeah. Okay. So is everybody okay with how do you figure out if something can have a proton that leaves? The acidic proton. It's kind of a Gen Chem thing, and I kind of just assume that you'll have a little bit of it. They're the ones that are going to be on something that has electrons withdrawing from it, right? So, for example, they're going to be on electronegative atoms, or they're going to be on something attached to an electronegative atom. Okay? On the other hand, how about that KOCH3? What is that? Mm-hmm. It's ionic, yeah. Yeah, and specifically when it falls apart, it's going to make a base, isn't it? Yeah. That's kind of like saying we have O minus CH3, isn't it? Okay. All right, so, by the way, that's actually why we're in solution for this. If you're wondering why the conditions were so specific. Yeah. Okay, so again, these are going to be KOCH3, ionic. We're going to have K plus and negative OCH3. We can actually ignore K plus for organic chemistry. We just don't care about it. It's going to be a spectator. It's never going to take the electrons back and make a covalent bond, right? So K plus just going to be floating around doing its own thing. All right. The next thing we need to do is the negative charge on the H2N minus. This is actually going to indicate the electron-rich state. And so right here we have the electron-rich site, this negative oxygen, right? It's going to donate electrons onto the electron-poor site, which is the hydrogen. The hydrogen needs to then shuffle its electrons off onto the next site, which is going to be the carbon there. That carbon will end up with a lone pair. Okay? Okay. We end up here. Anybody know what species that is? That's methanol. Like methyl alcohol, methanol. Wood grain alcohol. Okay. This one right here is actually the negatively charged cyanide. And if anybody's wondering, would this have other Lewis structures that are valid? Yes, it would. Okay. Like some of you may have been wondering, why doesn't the triple bond go over onto the nitrogen for negative charge there? You can. This has resonance structures. Okay. Okay. Oh, okay. Now let's talk about organometallic compounds. These are going to be sort of the where we'll start using metals bonding to nonmetals. And so these are going to have a metal atom that's bonded directly, typically to a carbon atom, because those are the ones we're going to be the important stuff. Specifically, the organometallic means carbon-containing bonded to metal, right? The carbon-metal bond is going to act as a polar covalent bond in most cases. You can think of it as just a very, very extreme polar covalent bond that tends to fall apart fairly easily. Okay? Okay, we good with that so far? Anybody realize I violated everything about general chemistry you know? I know. Dang it. Every time, right? The carbon is going to be a lot more electronegative than the metal. This is why it is going to be a polar covalent bond, is because the carbon actually will have the electrons around it quite a bit more. But it won't be such an extreme difference in these cases where they just fall apart to be ionic. Okay? And that's, again, because the carbon in and of itself is actually pretty close to being metalloid. Do you guys realize it's just one above silicon, right? Yeah. So it's actually pretty moderate. It's midway between the two different sides of the periodic table. There's an equal chance of it going left and right. And that's why it has the very moderate electronegativity, and it has a very small electronegativity difference with hydrogen. The organometallic compounds can be simply treated as electron-rich carbanions, carbanion being a negatively charged carbon. And so the negative formal charge actually appears on the carbon, and we can basically just treat this as this electronegative, this electron-rich species where we have a lone pair on the carbon, because those fall apart quite easily, though they are actually polar covalent bonds. They're not ionic. Okay? Okay. These are some different examples of this. This does not work with every metal that exists, though you can do some fun stuff to make metals that don't normally work. Okay? But that would be more of an inorganic thing that we'd talk about. So for these, most of these are things like lithium. There's the Grignard reagents, things like magnesium bromide. The magnesium having an electron negative group helps pull electrons towards it, okay, and helps it establish the polar covalent bond here. And then we have right here copper or lithium, both would work. In this case, we got the copper right there. Okay. Has anybody ever heard of lithium compounds?
Like batteries?
Not like batteries, but more like the lithium compounds you would take for like psychotic. No? Yeah. Okay. Yeah. It's okay if you haven't. But anyways, yeah. These are sort of the things why that's a thing and it works, and that's this, okay? Anyways, this is why copper is so detrimental to the environment, by the way. Did anybody notice there's a tub in the place we're putting all the copper stuff you guys use in biologies? In the fume hood? Yeah, this is actually why you don't want to release copper in the environment. Is it can make a bunch of organometallic, which are quite reactive. Yeah. Anyways, there you go. And in terms of batteries, by the way, you know you're not supposed to throw them away?
Yeah.
Yeah, this is why. Because eventually the lithium will leak out, and you can make organometallic compounds with react and make all sorts of problems. Yeah. So these are hydride reagents. They are not organometallic because they don't have carbon attached to it, right? But what they are is they're going to commonly function as reducing agents. They're going to include things like lithium aluminum hydride, LiAlH4. That's just how it actually looks. It is an ionic compound, actually. And so what you're looking at here is the lithium is the counterion here for the aluminum hydrogen. And this aluminum hydride has a negative charge. And the aluminum is actually having its electron density pulled away from it by the hydrogens. One of those can then pop off, and that will actually be hydride, which is an H minus. Everybody see the H minus okay? Okay. Now, to be honest, that's an incredibly reactive species, and it's unlikely that it actually exists as an H minus floating around, basically at all. Okay? It's very likely it's going to pop off and do the reaction immediately. Okay? But we do like representing these as H minuses like so, because it makes the reactions look easier. Okay. This right here, for example, this is sodium borohydride, NaBH4. And this, again, is another version of that. You will notice those are both the same group. Did you notice that? Yeah. Yeah. So, ooh, interesting, isn't it? Okay. Anybody have any questions about that so far? Okay. Keep in mind, both of these species I've been showing you, these are steps you can use to build up other mechanisms, and they're extremely reactive species that I'll be able to use later to do different reactions. Okay? I'm teaching you stuff you can plug in. Basically, I'm showing you hammers, how to use a hammer, and then we're going to use the hammer to build, right? I'm showing you a screwdriver, how to use a screwdriver, then we'll use the screwdriver to screw things on the hammer thing we just built. All right. So in a bimolecular nucleophilic substitution, SN2 step, a molecular species, which will be the substrate, undergoes substitution. Notice the name actually tells you a lot about it. Okay? And so S, substitution, N, nucleophilic. What do you think nucleophilic means? Nucleo, positive, right? Like a nucleus. Philic meaning likes, loves. Yeah. And so these are things that have typically a negative charge or electron rich. They like positive charges, and so they're going to attack things that have positive charges. Okay? So this is a nucleophile, thing that likes positive charges, doing the attacking. Okay? The 2 here means that's bimolecular. That has 2 molecules that have to come together to do this reaction. Okay? I kind of hinted something just now, didn't I? You think there's a possibility there's ones that have 1 molecule? You don't have to have 2 things coming together at once? Yeah. Yeah. So what's going to happen here is the nucleophile is going to attack a positively charged carbon. Can everybody see that okay? Okay. This is then going to have that substrate will have a leaving group. That leaving group is going to leave with a negative charge. Okay. And so the carbon chloride bond is going to give its electrons to the chloride, and that then leaves. Okay. Notice that the nucleophile had a lot of negative charge that could go over and attack that carbon, and that had that charge density to move around in it. Everybody see it okay? What do you notice about this leaving group here? Is chloride particularly stable with a negative charge? Yeah, that's why HCl exists, right? Chloride's actually quite nicely stable with a negative charge, isn't it? And that's why that's a good leaving group. So it's going to leave nicely with a negative charge, and it'll float around quite stably with a negative charge. Okay. Okay, so let's go ahead and look at another example of this. Again, this is an SN2 step. We have the nucleophile attacks the substrate. Again, this is going to be the positively charged site on the substrate. Positively charged carbon there. Okay, or an electron poor carbon, right? Okay. And then this is going to cause that to bond. Notice in this case, this started off with a neutral charge. And so if we donate an electron pair into a bond, what's going to happen to the charge on that nitrogen? You'll have a formal charge that's now positive, won't it? Okay. And then the leaving group right here is going to leave. That gained an extra electron by taking the electrons in that previous bond. And so that will leave with a negative charge here. Is everybody okay with that so far? Okay. Okay, let's look at the energy diagram for this. Many reactions are best thought of with energy diagrams. And so we go ahead and have the nucleophile again. The important thing about a nucleophile is it has a pair of electrons. It can donate into a bond. These are typically going to be things like a lone pair, but they could be things like a pi bond as well. Okay? They have to be delocalized electrons that can bend around, move around, reach out and touch something, right? Okay. And so these electrons are going to shift over. They're going to attack the electron poor site. They'll have a partial positive charge. This will cause what's called the leaving group to leave. Guess why the leaving group is called the leaving group? Because it leaves. All right. And so these will end up in a transition state right here. Remember, transition state is the activation energy you have to overcome, right? Where both things are actually starting to make bonds with it, the middle thing. See that? So in the transition state, both the leaving group and the nucleophile will both have partial bonds to that group, that R, that residue, that carbon usually. Okay? And this is that very high energy state. Now, could this leaving group stay on and the nucleophile pop off? Is that possible? Oh, yeah. Yeah, you can go both ways. In which case you get no difference, right? Nothing changes. Okay? And keep in mind, whenever we do reactions and we talk about these things, that stuff happens all the time. Reactions go back and forth on these energy diagrams. Okay? What happens is we have either something happens much faster. In this case, we're going to go faster this way than we would the opposite way. Anybody know why? Activation energy. The forward direction activation energy is much smaller, right? Yeah, smaller hill to overcome. The other part of this is actually exothermic. And so thermically, we're actually releasing energy, right? Yeah. Okay, so we have these partial bonds. One of them is going to fall apart. If this one over here falls apart, we go this way, right? We go to products. Okay. Okay, anybody have any questions about that so far? Okay, fantastic. Okay, so let's talk about the characteristics of that substrate. So in this case, the substrate of the molecule is going to contain a leaving group that's fairly stable by itself. The leaving groups have to be relatively stable with a negative charge for this reaction to get a really good yield. Leaving groups are typically going to be conjugate bases of strong acids. Why would that make sense? What is the strength of an acid? The weakness of its base, right? So the fact that it's a strong acid means that its conjugate base is actually very stable that way, isn't it? So it automatically was telling you that this entire time, wasn't it? Okay? Okay. So in this case right here, what does that look a lot like? Sulfuric acid, doesn't it? Yeah. And that's why that's a really good leaving group. Okay? It's because it's very stable with that negative charge over there. Right? At least compared to this species, which is less stable with the electron density around it. Okay? So, a nucleophile tends to be attracted by and form a bond to an atom that bears a partial or full positive charge. If it bears a full positive charge, then this does not need to be a very good nucleophile. In this case right here, we have a pretty high positive charge there. And so that's very easy to attack. Okay? On the other hand, if it has a partial positive charge, it's still going to be the place where you'll be attacking because, again, it's positive. It'll attract those electrons, right? Could you attack a site that's negatively charged? Would the electrons reach out and try to form a bond? No, that makes sense, right? Yeah. And most carbons are actually a little bit negatively charged, okay? Because they have hydrogens around them. Yeah. Okay. So some of the characteristics for those nucleophiles. These species are going to act as nucleophiles. They're generally going to have an atom with the following features. Fully negative charge or partial negative charge. They have to have some sort of concentration of negative charge around them. Okay? They're going to have a lone pair of electrons, or at the very least, they're going to have delocalized electrons. Okay? Because to form a bond, like, am I going to form a bond with my hands all curled in and doesn't open at all? Is that going to work well? No. How do you actually form a bond? You have something that can shift and move, right? And so you got to get in there and actually reach out. Okay? And so that's going to be incredibly important when we're talking about the characteristics of a nucleophile, right? That electron density has to reach in there, and it has to actually form a connection and bond with these things, right? Okay, so it has to be something you can manipulate, you can change, you can deform. Okay? Lone pairs by far and away the most common. All right? Basically, if you just go lone pairs of electrons and a negative or partial negative charge, that alone is going to get you about 80% the way there. Okay? These are some common negatively charged nucleophiles here. These are some common on-charged nucleophiles, and you can see here they're all things that have lone pairs. They have electron density around them. Even these on-charged ones have electron density, typically being donated by these CH3 groups, right? Or the hydrogens on the oxygen. Yeah. So they have a bit of electron density that's extra that they can afford to put out there. Okay? Now, there's one thing we haven't talked about, and I'll go into a bit more detail in a bit about it. But the better nucleophiles are going to be able to easily deform. Okay? What does that mean? If it's holding the electron density real tight to it, is that going to be able to reach out and touch things as easily? No. You need some room with that orbital, right? So it can come out and touch things. Okay? And so things that have more deformability, things like these bromides, chlorides, the sulfur here, see how sulfur shows up a lot? Okay? Well, sulfur has bigger orbitals. They can deform more, and so it can reach in there and touch things easier, right? Okay? Notice how things like fluoride isn't even in here, is it? F minus. What the hell? Where'd it go? It seems like from what I said, it'd be perfect, right? But remember, the F minus is actually really tightly packed in there, right? It holds on to those electrons great. And so it can't reach out and touch anything. Its orbitals just are too short to make overlaps and bonds. Okay? And so it doesn't show up on these things. And we can have other similar cases of that. where we've just concentrated that electron density too much. Those orbitals are not large enough to reach out and get us to places. Okay, sulfur, really good one though, because again, lower on the periodic table, right? Okay, so let's go ahead and we're going to do a problem in a bit. By the way, if you ever have a question that you're like, I don't want to interrupt the flow of it, okay, that's what these these Q&A slides are for, right? Is for me to handle any questions about a subject matter and for you to register if you haven't already. Okay, can CH4, excuse me, act as a nucleophile in an SN2 step? Why or why not? Okay, this is going to have a quiz in just a bit. Get an answer in your head. You all ready? Get ready, set, go. Dun, 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 dun. It's like a quiz show, isn't it? All right. Ooh, that one was close. No. Does CH4 have a lone pair? No, it doesn't have any delocalized electrons, right? So even if it has charge density, which it doesn't really have much charge density, it has a little bit, but not a lot. It just doesn't have any delocalized electrons that can reach out there and make a bond. Okay? Okay. Did that explain that for everybody? Everybody okay with that? Mm-hmm.
So if it was CH3, because there's a lone
Yeah.
in there,
CH3 minus is an excellent nucleophile. It doesn't hold on to its electrons very well. It's not super polarizable, which is the correct way of saying it has large orbitals that can deform. But it's very charge dense and it does not hold on to those electrons well. Yeah, and it has that lone pair that can reach out and form bonds. Okay. One of the ways you can think about these is if you remember your p orbitals in hybridization, that actually can help you out a lot here. So when it has an orbital that doesn't have a bond yet, but has electrons in it, that usually means it's going to be pretty good at acting as a nucleophile. And the only reason it wouldn't necessarily act as a nucleophile is just because it's like fluorine, where it's just too dang small to get in there. Yeah, it just can't reach out with that orbital. The orbital's too small, can't make the overlap. Okay? But in the case of like a CH3 minus, yeah, that'd be a good one. Okay, so let's go and compare proton transfer steps in the SN2 step. Did everybody see the analogy of these things when they were thinking about these? So there's a lot of overlap in the basicity of something and how good of a nucleophile it is, right? And in fact, nucleophile, meaning it likes positive things, and H plus is a positive thing. And so there's an incredible amount of overlap between a good nucleophile and a good base, okay? And so again, an electrophile is the opposite of that. I haven't brought that up yet, but an electrophile is going to be an electron poor species to which a nucleophile is going to form that bond. For example, that carbon here, this was a relatively poor electrophile, okay? Wasn't a great electrophile, but it's good enough. And so when we do these, this is going to be the analogy. We have acid base, right? Base is like a nucleophile. The acid is like a electrophile, isn't it? Okay. And in this case, the SN2 reactions for now are the only ones we'll talk about so far. We have the nucleophile. And again, nucleophile, many bases are also nucleophiles, right? It's many bases and nucleophiles are the same. And then we have the electrophile, and that's going to be that substrate electrophile analogous to the acid. What's the difference between an acid and a electrophile, by the way? Acids are very specifically just donating a proton, right? Yeah. Did anybody catch a little something interesting to all this, though? Anybody remember Lewis acids and bases? Did you guys cover Lewis acid and base? Yeah. So in a Lewis acid and base, what is a Lewis base? Lewis acid is an electron acceptor, isn't it? The Lewis base is then the electron donor. Yeah. Notice that these definitions almost exactly overlap with what we just talked about, right? We're just adding a little bit of caveats here and there. Yeah. So you're going to find that there's probably a good 30% of reactions in organic chemistry that could actually just be called Lewis acid-base reactions. Okay? And that material would have carried you through. Yeah, altogether, if you just do Bronsted-Lowry acid-base, Lewis acid and base, and just understand stability, you'll get about 70 to 80% of the questions right. Okay? Which is how I got through organic chemistry when I was an undergraduate. Where you guys have no idea how easy you have it with me. Or maybe some of you do. My organic professor gave us 6-page front and back full mechanism exams every week. Every week. On Friday, every week. We did 1 day of lecture, 1 day of review, 6-page front and back exam. Yeah, and sometimes we didn't get review. Always got the exam, though. By the way, she changed her office hours because of me.
Oh.
Yeah, she was ready to retire. And because it's useless to study if you're doing it every week, right? Like, you're not going to retain anything anyways. You're cramming every week. So I would just go in for the hour. She always had an hour or two before her class that she did office hours. I'd go in for an hour or two before the exam, and I would just drill her on the material. And I'd be like, I wouldn't even be nice about it, because I was nice the first couple weeks. But after taking 4 exams, where you had less than a week to prep for each exam, right? I was not nice about it anymore. I was like, quick, answer. Hey, you said it's easy. You said there's not much time. Go. Yeah. So she actually, the next semester, never offered another office hours. Actually, for the rest of her teaching career, never ever offered another office hour before any days she could ever have exams. Huh?
That's BS.
Yeah, honestly, that's like a tradition for organic professors that are getting ready to retire. Like, I don't know what it is, but I interviewed for several different jobs. I got offered a lot of jobs that needed organic professors when I was interviewing around. Part of the reason I'm here with you is I actually like the school and people here. They're very nice. But part of the reason is my mother's actually sick, and so I needed to stay relatively close. But so some of the jobs I got offered for, like, all of them are telling me stories, and all of them, like, the organic professor was kind of old and ready to retire, and they just went fucking crazy and tried to fail out their entire fucking class.
Really?
Why is that a trend?
You don't say.
Huh?
That's so accurate. Like last year.
Oh no, like Snelling thing, he was a particularly bad case of that. But
Yeah.
he was the 5th story like that I heard.
That's crazy.
Yeah. Like, I heard 5 of those stories, and who knows how many are like a thing. That, and the other one that I hear about from the past is, I'm not going to even, no. That's somebody else's story, and it's really messed up. Anyways, it's a pretty common story too. Okay, so draw the SN2 step. Mostly I'm not going to tell it because I don't want you guys to think, oh, that's an idea. No, that's not what I would be doing. Draw the SN2 step that's gonna, or that would occur between C6H5, CH2I, and CH3S Na. So there's several different things you want to look at and really tell you this is an SN2. Okay? It screams SN2. You ready for those hallmarks? Okay. Electronegative group that would be stable by itself. Iodide. Right? Strong acid. It's the conjugate base for strong acid, isn't it? It's stable by itself. It's electronegative, so it's pulling electron density from that carbon, isn't it? Okay? And so where are we going to attack? That carbon right there, right? That's where we're going to attack. Okay? The other part of this that's screaming SN2, SN2. Do you hear it? SN2. Okay. Is this sulfur here? That sulfur is actually an S minus, isn't it? Because sodium is a metal. Okay? And so you know that has a lone pair on it. It has a negative charge on it. It's sulfur. It's lower on the periodic table. And so it can deform its orbitals really well, can't it? And so this reaction right here, these ingredients, really you just need to understand the stabilities of things, right? And this screams SN2 mechanism, SN2 mechanism. Okay? Okay, so what is this mechanism going to look like? So the first thing we need to establish in an SN2 mechanism is the name, right? We're going to be substituting. It's going to have a nucleophile. That nucleophile is going to attack, and a leaving group is going to leave. That's where the 2 comes from. Okay? Okay. And so we're going to have our nucleophile, right? Okay. This right here, we had termed this the substrate before, but this is also an electrophile. Okay? That carbon there is an electrophile. Okay, so we have this negatively charged sulfur. It has 3 lone pairs. We take one of those lone pairs. We're going to attack the electrophile carbon. Okay? That's going to mean you have too many electrons around the carbon, don't you? And so one set of those electrons around the carbon has to go off onto something else. They're going to go off onto the most electronegative thing, which is the iodide. Anybody okay with that so far? Okay. And so we end up replacing the iodide with a sulfur, right? We go ahead and bring this right here with it. And it ends up on the other side so we can write it easily, right? Okay. By the way, when you do this on the computer, what you can do is you can actually copy all of that stuff, bring it over, paste it, and then you can actually just replace, because this is substitution, you just replace the leaving group with whatever you're substituting, right? So you can actually do these really easy. Okay? Okay. Did I lose people? Anybody get lost? Any specific place got lost? Okay. Everybody was okay of how I came up with benzene and all that? Okay.
We ignored the NA because it's positive, right?
Exactly. Yeah, that positive metal ion, that's going to be a spectator. Like, yeah, it's going to be over here, Na+. But these right here are a good electrophile, right? Or electrolyte, excuse me. Mm-hmm. And they'll stay apart. So, yeah. Yeah. Plus, we're organic chemistry, so we're going to just screw all that stuff, right? Yeah. If we did another step of this, by the way, we'd end up just ignoring all this stuff. We'd be like, I don't care about iodide. Yeah. Because it's always the organic carbon chains, right? Yeah. Is there any specific place that you can think of that got lost at all? Okay. So one of the important things is to get this really nicely in your head that SN2 tells you what happens, okay? The name in and of itself tells you, right? And so it's always nucleophile attacking, okay? That's what the N and 2 meant. Your end product is always a substitution of a leaving group. Okay? Okay. And that's the thing that's really going to help you out here, is because you don't need to memorize all these reactions individually. What you need is understand the name, nucleophile, attacking, and its substitution, right? And then understand relative stabilities, those same patterns we talked about in general chemistry with the periodic table, the same patterns that existed for acidity, basicity back in Gen Chem 2. All of that was building up to now, okay? So that you didn't have to try to memorize every single different electrophile and nucleophile and leaving group, okay? Which is really the really rough way to do this. By the way, if you're having difficulties with this, please make sure organic chemistry is a chemistry of practice. This more than anything, okay? What's going to happen is you'll be tempted to try to memorize every single one of these reactions. It is the wrong way to approach it. The correct way to approach it is to understand the reactions, why they happen, and then practice it, okay? Eventually what's going to happen is, for some of you, first assignment, it's going to happen. For some of you, it's going to be the 20th time you try it. But eventually, you're going to have these things click, and you're going to look back and go, why the hell was this so difficult? This doesn't, oh my God, old me. Kind of like what happens in lab, when you look back at the lab, and you're like, really? Really? That took you 3 hours? Really? Like the crystallization, right? You look back at that, that took me 3 hours? Yeah. Okay. You all have a great day. Let me know if there's any questions or anything. I guess there's the slide QA. And we'll start here next time. What?
Our last semester when we did crystallization, she messed up our experiment.
Only one group out of the whole lab, even the teacher did it right.
What? How is that?
Because whenever she was filtering out the solution, she put that thing on it. What is it called? Like,
The vacuum filter?
yes.
Yeah,
And she did. It was too strong, I guess, for what we were
It was
doing.
really sucking
Oh.
And so it was literally taking
It's too
everything.
strong.
It was taking everything with it instead of like filtering it out better. So
What filter did she use?
We were just using the little circle
we had,
filters.
yeah, the little circle ones, like the paper.
Yeah, it was just little white circle.
Were you
filters.
cooling it down first?
Yeah.
Oh, you were using the full-size ones.
Yeah.
Yeah, I think so.
And we would filter it out. And
Oh,
then
and
was-
she didn't have you do the decanting, did she? Yeah,
It was
so
taking too long, so she put the vacuum on it, and it like sucked it all through the thing instead of filtering it out right.
you can't actually do it, quote unquote, too fast or have. So the only way you can have too much vacuum is actually for